Okay, so number 18, what makes this problem different is that it's sort of a domino effect. All the problems up to number 18, everybody's attention here? All the problems up to number 18 you're talking about one object that goes from one position to another. And if work is done in between your start and your end position, you include it. If the work is not happening in between your start and your end position, you do not include it. Now in this problem, we're actually getting the energy from something else. When I write my conservation of energy equation, I'm going to be writing it for the stake. The stake is what is being driven into the ground. Originally, it's just on the ground, and then we drive it with one blow, 1 inch into the ground. But that energy is coming from something else. So again, it's like a domino effect. Something else is creating the energy, and then that part of that energy, in this problem, 40% of the hammer's kinetic energy is converted into the original kinetic energy of the stake. So what I'm going to be doing is this is going to be my substitution. I'm going to be substituting in 40% of the hammer's kinetic energy for the original kinetic energy of the stake. So in doing this problem, and also notice that this is in English units. So if it's in English units, usually we need the mass. They gave me the weight of the hammer, so that's going to have to be converted into a mass. And since we're in the English system, what is our unit for mass in the English system? Slug. So that's going to have to be slug. And so actually our unit for energy in this problem would be foot-pounds. It's going to be foot-pounds, not joules. So I'm going to begin like I've begun every other problem. I'm going to begin with the law of conservation of energy equation combined with the work energy transfer theorem. So there is the equation that we're starting with. Now, in this problem, the stake moves 1 inch into the ground. So it's already starting on the ground, and then we're moving it further into the ground. So even though it's vertically moving an inch down, it started on the ground. So there's no room for it to free fall through the air. So that means that there is no potential energy in this problem. We're just looking at the kinetic energy. Now, once the stake is 1 inch into the ground, it will no longer be moving. So if it's no longer moving, then we know that the final kinetic energy is 0. So the only things I have left here are KO plus work equals 0. And since we're not getting the kinetic energy, we're getting the mass. Well, we can get the mass and the velocity. And since we're not getting the work, but we're solving for force, and we know distance, we know it's going 1 inch into the ground. So since we know the distance and we're looking for the force, I am going to be replacing these. Now, because it says that 40% of the hammer's kinetic energy is converted into the original kinetic energy of the stake, that's the original kinetic energy of the stake, I'm going to be replacing that with 40% of the hammer's kinetic energy. So it's like a little substitution here. I'm going to have that this is going to be 40% of the kinetic energy from the hammer. That is going to replace the original kinetic energy of the stake. So I'm going to write that as 0.40, and I'm going to multiply that by 1/2 the mass of the hammer times the velocity of the hammer squared, plus the work. Now work is force times distance, and that equals 0. So if I rearrange this equation to solve for the force, I'll have my answer. So I need to move this term to the other side. So since it's a positive on the left side, it's going to be a negative on the right side. Also, when I bring it over, I might as well make this into one number. So half of 0.4 is 0.20. So I'm going to move that to the other side, And again, I'll be solving for force, so then I'll be dividing by D. So the algebra is going to be, F is going to equal 0.20, because I'm taking half of 0.40, mH VH squared divided by D. And all I need to do is get those three numbers. I already have the velocity of the hammer in the units I want it to be in, 25 feet per second, but I have the weight of the hammer, not the mass, so I need to get the mass of the hammer. And I have the D in inches. That needs to be in what units? Feet. So I need to do two conversions here. So I am going to, let's see, I'll do the mass of the hammer over here. So the mass of the hammer is going to be the weight of the hammer divided by G. So the weight of the hammer is 5 pounds. Now I'm not going to write it as a pound. I'm going to write it as 5 slug feet per second squared because I want to see that I get my answer in slugs. And so, yes. Right, exactly. Yeah, that's supposed to be negative. And actually, though, when I did this problem earlier, I had the negative there. But then the answer I didn't write as a negative. And I said that even if you didn't have the negative, I could not really take off because they do use the word a resistive force. So we know by definition it's going to be negative because it's a force resisting the motion. So since the question is asking for obtain the average resistive force, then by definition it would be a negative. Yes? What's that? Over here? Because that's what the definition is of the definition of a pound is a slug foot per second squared, just like the definition of a Newton is a kilogram meter per second squared. So a Newton's a kilogram meter per second squared, and a pound is a slug foot per second squared. So now we're going to take that, and we're going to divide that by what? What's the number in the English system for gravity? 32 feet per second squared. So if we solve that, 5 divided by 32, I think is, what, 0.156? So 0.156 slugs, that gets us the mass of the hammer. Now we need the D. We need that in inches. So I'll do it right next to it. So the, so the D, let's see where I'll do it. I'm going to do it over here. So the D is 1 inch, and I want to convert that into feet. So I'm going to go from inches to feet, 12 inches in 1 foot, so that's going to equal 0.0833 feet. 1 divided by 12. So I have all the numbers now, and I can just plug it into my equation. So F is going to equal minus 0.20 mass of the hammer, velocity of the hammer squared, divided by D. So the mass of the hammer is 0.156 slugs. The velocity of the hammer was, what was it, 25? 25 feet per second. And the D is 0.0833 to get 3 significant digits, feet. So if you look at my units here, I'm going to get the feet down here are going to cancel one of the feet, but remember that's squared. So I'm going to get slug feet squared per second squared divided by feet is slug feet per second squared. and that's a pound. So the answer will come out negative, and what did I say? Negative 235? So negative 235 pounds. Again, they do specifically identify it as a resistive force, so that would mean it has to be negative. It's a force that's reducing the amount of energy that we have. Any questions? So again, there's another one like this, number 22, where some amount of energy from something else gets transferred into the object that we're using for our law of conservation of energy equation.